So we saw one derivation of PCA. Let's see now another derivation that will take a different path to achieve the same results. So basically, we will develop the PCA again, but now looking at a different approach, we will search for transformation Z equal to W transpose X, where variables Z are uncorrelated. So we are looking to decorrelate the variables, basically. So for this, we are looking for a W so that the covariance of Z is equal to D prime, and all this is diagonal. Let's suppose C, which is a matrix of D by D, where column Ci is the eigenvector I of S, and S is the estimator of the covariance matrix. So if we go that way, we just say, okay, every column in my matrix C is one eigenvector of S. So we have all the eigenvectors put one on the side of the other. That gave us the big matrix C. And given the definition of eigenvectors, which make a basis, we know that basically C times C transpose, which is equivalent to C transpose C, all this is equal to the identity matrix. And as such, we can just simply say that the S is equal to S times C transpose, because this is corresponding to the identity. But if we develop this a little more and we just expand the vectors composing the middle matrix C, we will get all these different eigenvectors. And we can get into something like this. So we just multiply every small C vectors by S. We get SC1, SC2 up to SCD times C transpose. And knowing that, in fact, when we multiply the matrix S by one eigenvector, this is corresponding to the eigenvector times the eigenvalue that is associated to it. So basically, we will get this, which is equal to that, get this equal to that, get this equal to that. This is the basics from the eigenvectors analysis of a matrix like the covariance matrix. And so if we expand even a little more with the C transpose, we get this kind of result. So we get something like lambda 1, C1, C1 transpose, plus lambda 2, C2, C2 transpose, up to lambda D, CD, CD transpose. So this is an expansion, basically, of the covariance matrix, where we will compute everything that way. So we are able to kind of develop or decompose the covariance matrix that way. And this thing corresponds basically to, so this thing is equivalent to say something like we have a result that corresponds to C times D times C transpose. So here, what is D? D is diagonal, and it contains, in fact, the eigenvalue. So basically, it's a diagonal matrix of size D by D with only values on the diagonal. Out of diagonal, it is 0. And we have on each, on the diagonal, the lambda 1, lambda 2, up to lambda D, which are basically the eigenvalues of our eigenvector eigenvalues decomposition of the covariance matrix. So we call CD C transpose as the spectral decomposition of S. So since C is orthogonal and C transpose equals C transpose C equal to I and all this, we can just move things around like that. So we just, okay, we have this spectral decomposition here. This is our starting point. So now let's multiply each side by C transpose and C here, C transpose and C here. So we have these things that we multiply the same way from both sides. So the point here is that this is equal to identity. This is that also equal to identity. So basically, we are simplifying this to a D here. So we have the D here that correspond to C transpose SC. And as such, we know that the covariance of Z is corresponding to W transpose SW. And we want this covariance to be diagonal. Thus, a way to achieve that is to set W here, the transformation we are looking for, as equal to C. Why? Because we can get something like that. So we can get things like CTSC is equal to the diagonal. Anyway, to the eigenvalues, sorry. So this is equal to the eigenvalues of our eigenvector eigenvalues decomposition of S. This is the way we are setting our vector W, our weights, as corresponding to the eigenvectors.